Welcome back to the course, Multi-Layer Neural Network Training and Testing Implementation. In this lesson, we will have an introduction to neural networks. We will discuss neural networks conceptually. We will discuss what are neural networks and what is it that they do. First, we will discuss the problem that neural networks address. What problem do they attempt to solve? Then we will look at how neural networks attempt to address this type of problem. This discussion will be from a high-level and abstract point of view down to a more detailed view. Lastly, we will look at the structure of a neural network from a high-level perspective. The structure of a neural network will be discussed in greater detail in the next lesson. So now we will ask the question, what problem do neural networks address? To answer this question, we'll first consider a system, the nature of which is unknown. When observing this unknown system, some values x are observed. These x values are somehow associated with the system. In addition, when the x values are observed, the y values are also observed. I used the vague term observed, but you could instead say measured or recorded. Physical values are typically measured, but other types of values are simply recorded. Examples of physical values are pressure, humidity, height, length, etc. And examples of recorded values are the closing price of a stock, the length of a day, etc. The point is that there are observed values x and y, and the system somehow relates them. Or in other words, the y values are a consequence of the x values related in some unknown way by the system. Note that the x and y can be a single number or an array of numbers. Simply stated, the purpose of a neural network is to determine what this relationship is. The neural network determines this empirically by being presented with a set of examples x and y, such that when presented with another yet unseen value of x, the neural network can predict with an acceptable degree of accuracy what the corresponding value of y should be. The determines empirically part is referred to as training. During training, the neural network is presented with a large enough set of x and y examples so that the neural network can determine or learn the relationship. It does this learning by comparing the expected value of y with the value of y prime the neural network outputs for the given value of x and adjusting its reasoning to make a better match in the future. This is referred to as supervised learning. The set of example x and y values during the training process is referred to as the training set. The prediction part is referred to as testing. When presented with another set of x values, the neural network outputs corresponding values of y prime that are close to the expected values of y. The set of examples x and y values during the testing process is referred to as the testing set. Neural networks address this so-called prediction problem. There are generally two accepted types of prediction problems, classification and regression. In classification problems, y will be a class identifier, and in regression problems, y will be a real number. Note that in either case, y is a number. In the case of classification problems, the class identifier can be represented as an integer. For example, in the case of true or false, true can be represented by the value 1, and false can be represented by the value 0. As we will discuss in more detail later, there is another way to represent class identifiers, which is by using so-called binary class vectors. These binary class vectors identify the class by having the value 1 at the index corresponding to the class, and zeros at every other index. The index I of the value 1 is the class identifier. Another way of looking at a system is to think of the system as a function. When the value x is observed, it can be thought of as having been processed by the system function f of x that produced the observed value y. Systems, in particular natural systems, are often dynamic, nonlinear, and stochastic, that is, random. A very good example of such a natural system is the atmosphere and weather. As with systems such as the atmosphere, weather, and climate, the approach taken is to mathematically model the system. Models can be deduced theoretically from first principles, or they can be arrived at empirically through experimentation. Another way to empirically derive a model is to formulate a mathematical parametric structure for the model, and through experimentation arrive at suitable values for the parameters. That is essentially the approach taken with neural networks. The neural network model, or in other words, its structure, is a parametric function that was deduced theoretically by applying calculus to progressively minimize the errors between the expected value y and the value y output by the neural network as a result of processing the input value x. In this course, the discussion is first described in mathematical terms, which is then converted into code. The beauty of neural networks is that they can, at least in theory, be applied to any prediction problem. The neural network model is a system of linear and nonlinear functions. As shown in the diagram, these equations are divided into layers that progressively process the input value x to compute the output value y. As we will discuss thoroughly, each layer's function is a parametric linear equation and a nonlinear function. The parameters of the linear equation are the layer's connection weight matrix, denoted by uppercase W, and the neuron bias array, denoted by lowercase b. The nonlinear function is referred to as an activation function, denoted by alpha. The training process involves adjusting the weight matrix and bias array values in a process referred to as backpropagation and gradient descent. In a higher level of learning, the specific activation function to use could also be a parameter, but that is outside the scope of this course. In the next lesson, we'll take a more in-depth look at the structure of a neural network so that when we look at the mathematics of training and testing, and then the implementation, we'll have a very good understanding of all of the components of a neural network and the terms used to refer to them.